Good morning, children. Last class we have seen Galilean transformation equations, and today we are going to see Lorenz transformation equations. The improved version of Galilean transformation is known as Lorenz transformation equations because some defects were there in Galilean equations, and these defects has been removed by the Lorenz transformation. So let us consider two systems S and S dash. In the system S, we are taking three axes X, Y, Z and the observer O. Likewise, in the system S dash, we are taking the three axes as X dash, Y dash, Z dash and the observer is at O. Now the frame S is unaccelerated and the frame S dash is accelerated. That means the frame S is at rest and the frame S dash is moving with respect to S at a velocity V. Now let us consider a particle P at a distance X dash from the Y axis in the frame S and at a distance X from the S frame. So the distance travelled by the observer from O to P is R. We know velocity is equal to distance by time, or distance is equal to velocity times V. Distance equal to velocity times time. Therefore, now we are going to consider two systems. One system is S and another system is S dash. Before movement, the two systems are in coincidence with each other. That means on X by Z, X dash by Z dash is lying. Only when it is getting accelerated, S remains still at rest and S dash is moving from S at a velocity V. So based upon that, we are going to write the distance equation, and from that we are going to derive three important equations. I told you that is nothing but length contraction, time dilation and mass variation. So the first distance between the point O and R is written as R into C, where I told you distance is equal to velocity into time. So distance R is equal to C. C is the velocity of light and T is the time taken by the particle to travel from O to V. And the equation for R can be written as X, Y, Z. So R square is equal to X square, Y square, Z square. Therefore, we can write this as X square, Y square, Z square is equal to C square, T square. Likewise, in the second particle it is given as distance O dash to P is marked as R dash. R dash is equal to C times T dash. Therefore, that can be written as R dash square equal to C square T dash square. Therefore, we can write the equation as X dash square plus Y dash square plus Z dash square is equal to R square equal to C square T dash square. When the particle is moving, they are at an equilibrium state, means the two systems are equal. Therefore, we can write X square Y plus Z square is equal to C square T square is equal to X dash square plus Y dash square plus Z dash square minus C square T dash square. The particle is moving only in the X plane, whereas the Y plane and Z plane are at rest. That means there is no motion. When there is no motion, we can write Y dash equal to Y and Z dash equal to Z. Therefore, only the X factors remain and the Y factors and Z factors get cancelled. Therefore, the equation is X square minus C square T square is equal to X dash square minus C square T dash square. So this is the form of an equation. We have to form a solution. This equation is in the form of a simple harmonic. Therefore, we can write the solution because the velocity is very much less than the velocity of light. So X dash equal to K into X minus Vt and T dash equal to A into T minus Bx, where A, B are constants and K is the wave constant. So substituting these values, we can write the above equation as X square minus C square T square equal to K square into X minus Bt the whole square minus C square A square T minus B minus X the whole square. Now we have to expand K minus Bt the whole square in the form of A minus B whole square, and we have to expand T minus Bx in the form of A minus B whole square. When you expand these two, substitute, you will get one equation. After getting that equation, when you equate the coefficients, you will get K square minus C square into A square minus B square equal to 1. K square V minus C square AB is equal to 0. So we have to equate the coefficients of X square, equate the coefficient of X, equate the coefficient of constant. When you equate all these three coefficients, you get these three equations. When you solve these three equations, you find the value of the constant k is equal to a equal to 1 by root of 1 minus b square by c square, and b is equal to v by c square. So you found out the equations, you have found out the constant values. After finding out the constants values, we have to substitute these values, and from that we will be getting Lorenz transformation equations. So we can now write as x dash is equal to x minus vt into root of 1 minus v square by c square, and t dash is equal to t minus v into x by c square divided by root of 1 minus v square by c square. So we are getting the value of x dash and y dash. But there is no motion in y plane, so y dash is equal to y. There is no motion in z plane, so z dash is equal to z. These are the raw equations of Lorenz transformation equations. Therefore, Lorenz transformation equations are nothing but all these put together is known as Lorenz transformation equations. X dash is equal to x minus vt by root of 1 minus v square by c square, y dash equal to y, z dash equal to z, and t dash equal to t minus v of x by c square in root of 1 minus. These equations are known as Lorenz transformation equations. And we have got Lorenz inverse transformation equations. We have got what? Lorenz. Also we have got Lorenz inverse transformation equations. The question will be only to derive Lorenz equations, but suppose if they are Lorenz inverse transformation equations, you need not worry. Just say change in symbol. These are Lorenz transformation equations. Just a change in symbol will give you that's all. So you write x is equal to x dash plus vt by root of 1 minus b square by c square, y dash equal to y, z dash is equal to z, means y is equal to y dash z. So opposite to this, t dash is equal to t plus v of x by c square divided by root of 1 minus v square upon c square. That's all. So what you have derived is Lorenz transformation equations. Just to change the sign, in place of negative sign you are getting positive sign, in place of y you are getting y dash, z you are getting z dash, x you are getting x dash, t you are getting t dash. That's all. So here you have got a negative sign, it will become a positive. These are known as Lorenz inverse transformation equations. So you have to draw the two systems. From the two systems, you have to see what is meant by R is equal to Ct, R dash is equal to Ct dash. Set up an equation, then equate the equation. From the equation, you have to write the two solutions. After writing the two solutions, you have to equate the equation. Then you have to equate the coefficients for x square, x and constant. You will get three equations. Solve these three equations. You will get the value of k, a and b. These are the constants. When you substitute all the values of k, a and b, you will get four equations, because the motion is only in x plane. There is no motion in y and z plane. Therefore, x dash is equal to x minus vt divided by root of 1 minus v square by c square. T dash is equal to t minus v of x by c square equal to 1 minus v square by c square. Y dash equal to y and z dash equal to z. These are known as Lorenz transformation equations. Based upon that, we can write Lorenz inverse transformation equations, which are written on the board, and that is only with a negative sign. So there was first some equations that is known as Galilean transformation equations. The Galilean transformation equations were not able to satisfy that they are moving with the velocity of light. So there was another scientist, both of them Lorenz and Fitzgerald, solved the problem, and they have found out these equations, and these equations are the now followed equations, which are given the value of this x dash, y dash, z dash and t dash. Based upon Lorenz transformation equations, we are going to take the next steps in finding out length contraction, time dilation and mass variation. So up to this we have seen in the class. The others we will see in the next class. Thank you.